All right, let's talk about the atomic glue. It's this incredible, invisible force that holds literally everything in our world together. We're going to dig into the really big question of why things even exist as solids or liquids, and not just, well, a puff of atomic dust. I mean, have you ever really stopped and wondered about that? Why is the world solid? Why is that chair you're sitting in, the air you're breathing, why are you not just a big chaotic cloud of disconnected atoms? What's stopping the whole universe from just dissolving into dust? Well, it turns out atoms are kind of social creatures. With very, very few exceptions, you almost never find them flying solo. They are constantly clinging to other atoms, forming the molecules that make up, well, everything. And that connection, that clinging together, that's the atomic glue we're here to figure out. So, to crack this mystery, scientists first had to understand what you might call the atomic social scene. You know, who wants to connect with who, and who's perfectly happy being a wallflower. And this is where we find our first huge clue. See, most elements are what we call reactive. They're buzzing with energy, always looking to hook up with other atoms. But then, there's this small, exclusive club of elements that are perfectly content, totally stable, and, well, completely antisocial. So on one hand, you've got the total socialites of the periodic table, like sodium and chlorine. They are so reactive they'll bond with just about anything. And on the other hand, you have the quiet loners, the noble gases, like neon and argon. They've achieved this kind of perfect stability that all the other atoms are jealous of. Understanding that difference was the key to the whole thing. So, back in 1916, two scientists named Kössel and Lewis finally cracked the code. They realized it all comes down to the electrons. The noble gases? The reason they're so stable is that they have a perfect, full outer shell of 8 electrons. We call that an octet. And it turns out pretty much every other atom is on a desperate quest to get that same stable setup. This simple idea is called the octet rule. Okay, so if you're an atom, how do you get a perfect octet? Well, the first strategy, it's not exactly subtle. It basically involves a little bit of theft. We're going to call it the Great Electron Heist. So meet our first character in the heist, sodium. If you look at its electrons, it's got these nice, stable inner shells. But then there's this one lonely extra electron in its outermost shell, and it hates it. That one electron makes the whole atom unstable. If sodium could just ditch that one electron, its new outer shell would be a perfect, stable octet. It is desperate to get rid of it. And every good heist needs an accomplice, right? So meet chlorine. Chlorine has the total opposite problem. It has 7 electrons in its outer shell. It is so close to that perfect 8. All it needs is to find and grab one more electron from somewhere. Yeah, you can probably see where this is headed. When these two get together, it's a perfect partnership. The electron literally jumps from sodium to chlorine. Sodium is more than happy to give it away, and chlorine eagerly snatches it up. But here's the really cool part. The aftermath. Since sodium lost a negative electron, it now has a positive charge. And since chlorine gained one, it has a negative charge. And what do we know about opposites? They attract. That powerful pull is the bond. And just like that, we have our first type of atomic glue. It's called an ionic bond. It's that powerful electrostatic force that holds those oppositely charged ions together. It's not a physical chain, but an incredibly strong attraction born from that little electron heist. Okay, so the whole heist thing works great when you've got a willing giver and an eager taker. But what happens when you have two atoms of the same kind and neither one wants to give anything up? Yeah, that calls for a totally different strategy. Something more like a cooperative partnership. So let's go back to our friend chlorine. What happens if it bumps into another chlorine atom? Now we've got a problem, right? They both desperately want one more electron to be stable, and neither one is going to just give theirs away. A heist is completely off the table. So what's the solution? Well, the solution is actually pretty brilliant. They negotiate. They decide to cooperate by sharing electrons. It's this fantastic compromise where both atoms get to achieve their goal of having a stable outer shell. And this is our second type of atomic glue, the covalent bond. By sharing a pair of electrons, both of those chlorine atoms now get to count those shared electrons as part of their own shells. So each atom effectively feels like it has a stable octet. And that sharing creates a strong, stable bond between them. And this sharing agreement is super flexible. Atoms can share one pair of electrons, which makes a single bond, like we saw with chlorine. Or they can share two pairs to form a stronger double bond, like carbon does with oxygen in carbon dioxide. And for a really, really strong connection, they can share three pairs in a triple bond. That's actually what holds the nitrogen molecules in the air you're breathing together so tightly.
So we've got giving and we've got sharing. That pretty much covers it, right? We've solved the mystery of the atomic glue. Wow, not so fast.
Look, this simple and powerful idea of giving and sharing electrons, what's known as the Lewis approach, was a monumental step forward in chemistry. But like all great scientific theories, it didn't answer everything. In fact, it opened the door to even deeper questions. The source material puts it perfectly. This theory is fantastic for counting electrons and figuring out who bonds with whom, but it tells us absolutely nothing about the beautiful and complex three-dimensional shapes that molecules actually form. I mean, why is a water molecule bent into that little V shape, while a carbon dioxide molecule is a perfectly straight line? And why do some bonds need way more energy to break than others? For instance, the bond holding two hydrogen atoms together is much, much stronger than the one holding two fluorine atoms. These simple models just can't explain it. Answering these deeper questions required new, more advanced theories, things like VSEPR theory, which is all about explaining those 3D shapes, and valence bond theory, which digs into the energy and length of bonds. And the cool thing is, these theories don't replace the octet rule, they build right on top of it, adding new layers of detail to our understanding. And that's really the beauty of it all, the entire mind-boggling complexity of our universe. From a single grain of salt to a swirling galaxy is all built on atoms following these few simple rules about giving and sharing. It just makes you wonder, doesn't it? What other elegant, simple rules are out there, governing everything around us, just waiting for us to figure them out?